Your hook. Why is this man safe? Why would you be safe inside of a car or an airplane being hit by lightning? Stay tuned. Okay, I have two charges and I want to talk about the field produced by these charges. You've just done a lab. I don't want to spoil the lab, but I do need to talk about certain aspects. I would hope in the course of doing that lab you got a field line that looked like this. What went on was you put a positive test charge and it followed this pathway, which by the way is not a conic section. It's not a parabola or an ellipse or a hyperbola, and it's not a catenary either. I'm not sure that it has a name. But let us suppose that you put a test charge at this location so that it would be repelled by the positive charge while simultaneously being attracted to the negative charge. You assume that these two have the same amount of charge, but that this one is twice as far away as that one, which means that the force, yes, you got it right, would be a quarter as strong. So to the negative there would be an attraction, and it would be a quarter the magnitude of this repulsion. Both of these forces acting simultaneously, you superimpose them, and the resultant force is one which goes tangent to the curve. Let's try it again. Okay, tangent to the curve goes the magenta one. Let's put this one right so that it is equidistant from the two. Again, repulsion from the positive and attraction to the negative, but this time of equal magnitude. And if you superimpose them, the resultant is a vector which again goes tangent to the curve. This unique curve, whose shape I do not have a name for, is formed because our definition of field is what it does to a test charge, and the direction of the force on the test charge at every point is going to be tangent to the curve. Now, here would be a pair of charges. You could tell me, are they like or opposite charges? And I hope you see the pumpkin of embrace there, that they are opposite charges. And if you put a yeah, what else do I need to say? That they are opposite charges when you see them being attracted, this unique shape that you have here. But again, the actual shape of these curves is determined by that superposition of attraction and repulsion from these two at every location. Okay, here's a charged object sitting in the air, losing its charge. And what does it mean that it's losing its charge? Well, what it means is it's giving up its charge to the air. It is not surrounded by nothing. It is surrounded by atoms, which might be locally charged, what we call polarized atoms. Water is the most notable example of a polarized atom. Or it might be that they're not polarized, but because of the field, local charge gets induced on them. In either case, what's going to happen is that the local charge would be induced, opposite charge closer, and they would be attracted and they would come over and touch. And in the act of touch, there is the possibility of the exchange of charge. The fact is that it seems to be very difficult for atoms to exchange charge, that this one here might exchange its charge. And if it did, then it becomes like a like-charged ion to the charged object, and as a consequence, it would be repelled. And what is, in effect, what has happened is one of these positive charges has gone away. In fact, what really happened was that one of them was canceled by an electron from this guy, and this one ran away. But it's the effect of the charge disappearing. Well, the fact that this happens so slowly means it must be difficult for this exchange here. We rather think that it is water molecules that are the ones that do it. That's why drier air is a time when you would keep your charge better. There you go. Okay, new topic. I have a conductor, a metal lump here. Maybe it's gold. Heavens, got your attraction there. And it is neutral. Now, neutral, of course, does not mean that it is without charge. It just means it has equal amounts of both kinds of charges. Now, suppose there was an electric field inside of that conductor, causing positive. We'll say green is positive and red is negative. The positive charges would be pushed in this direction, and the negative charges would be pushed in this direction. The negative charges being the ones that move more easily. They're going to go jumping over here as a result of that field. But because of this field, there has been a rearrangement of charge and an inducing of local charge, and it is such a rearrangement that the field, which would go from positive to negative, is created. That this blue field caused a rearrangement of charge which creates this field. And the net field is going to be the sum of those two fields. And so what has happened is that because of the rearrangement caused by this field, it weakens this field. But the rearranging will continue until finally sufficient charge has moved that the field from the rearrangement of charge finally equals the field that was causing the rearranging, and then the net field is zero. And that all happens in a microsecond or less. And so I would state that inside of a conductor there is not any electric field, which sort of feels like we're getting closer to why that man was safe in there. But wait, there's more. That if there were a field, it would cause the charges to rearrange until there was not a field. And because it's a conductor, that means they do rearrange when subjected to a field. Okay, no field inside of conductors. But what about at the surface of a conductor? What does the field look like? Well, suppose the field was going at that direction, at that location on a conductor. Well, that field would have a component tangent to the surface and a component perpendicular to the surface. This component here, let me move that over. This component here is going to act on the charges that make up this material. It's made of atoms with electrons and protons, and the electrons, because it is a conductor, would tend to be pushed in this direction by this component of the field, whereas the protons would be left behind. But once again, you get a field in the contrary direction to that, and which would weaken this field. As long as there is a net field in that direction, the rearranging will continue until there is not any field tangent to the surface. Again, happening very, very quickly, nanoseconds. And so we state that inside of a conductor there is no electric field, and at the surface of a conductor all electric field is going to be radial or perpendicular to the surface. That if there was an element of field that was tangent at the surface, that would cause this rearrangement until there was not an element tangent to the field. What about the arrangement of charge on a conductor? Again, this thing is a conductor even though it's not yellow. Well, to be a conductor means charge can move. These like charges are going to have a repulsive force on one another, and since they're on a conductor, that repulsive force will result in them moving. And they will move all the way as far apart from one another as they can get. You might think that some wise charge would say, but if I stay in the middle, I'll be further away. But that doesn't happen. The repulsive force causes them to move until they are on the outermost skin of this conductor. And so there's the other piece of your safety inside the automobile and that man, that all the charge goes to the outside. Next year in AP Physics, I will give you a much more profound reasoning for why the charge is all on the outside, but I think this works pretty well. What about if there is a void? Let's make it a bigger void inside of this thing. Would some of the charge go on this skin? And the answer is no, and you just have to take it from me that it does not. That all of the charge is on the outermost edge of a conductor, if there is a net charge on the conductor. What about this arrangement, where we have lost the symmetry we had before? Well, again, the charges are going to want to get as far apart from one another as they can. They will be repelled out to the outermost skin. But this time we do not have the symmetry that we had last time, and so there will not be a symmetrical arrangement of the charges. And what we will find, and you're just going to have to take it from me, is that at the place where the radius of curvature becomes the smallest, there you are going to have the highest concentration of charge. I want you to know that. On a non-symmetrical object, the net charge will be on the outermost edge, and the highest concentration will be at the point where there is the smallest radius of curvature. Which is why, if you stick out your finger at the Van de Graaff generator, the lightning bolt will jump to your finger. But if you don't stick your finger out, if you keep it in a fist so you are more symmetric, then you do not get the high charge concentration build up, and you do not get the spark jumping as soon. So again, he is safe because there is no field inside of this charged conductor. He could even touch the inside because all the charge would be on the outermost edge. If he stuck his fingers through and touched the outside, then he would get a great big shock. And the same goes for you in a car. If you are being safe by being inside a car while it's being hit by lightning, and you roll down the window and reach out and touch the outside of the car, you get zapped. Okay, last topic, lightning bolts. Lightning. That this cloud comes to be charged. Oh my, I got too much. Let's see if I can just get the charges. There we go. Okay. It comes to be charged. Sometimes it comes to be charged negatively. Sometimes it gets to be charged positively. That it has to do with the water moving through the cloud. Um, that's a kind of a rubbing event. So again, triboelectricity occurs and charge gets rubbed off and on. But let us presume that this cloud, at least the bottom of this cloud, has come to have a positive charge. That it sometimes the top of the cloud is negative and the bottom is positive, and you get lightning jumping within a cloud, or you get it jumping from one cloud to another. But we want to deal with the earth here. Now, there is, come on now, here you go. This positive charge here in this thunderhead is going to, is going to cause a rearrangement. The field from this is going to cause a rearrangement in the charges here on the Earth, and it's going to cause a net opposite charge here on the Earth, and so you will get the negative and the positives looking bad. If you have something protruding from the Earth, like a house, that represents a non-symmetry. It's also closer to the cloud, and for multiple reasons you get a high charge concentration at that point, and that is where the lightning is likely to strike. And so if you find yourself in a situation where lightning is possible, you ought to get as low as possible. You do not want to be the tallest thing around, or lightning will hit you. Well, add to this a lightning rod, which is a conductor. This represents the grounding, so we electrically connect it to the earth. This is going to go higher than the house. It's going to be more pointed than the house, and so you are going to get this intense charge concentration at the lightning rod. And what most practitioners of lightning safety will tell you is that this then is the place that the lightning jumps to and thus protects your house. The other thing, and this was, I looked online and that's what everybody was saying. They also said that the current that flows here can be like 150,000 amps. That much current flowing through these wires would vaporize these wires as they sit there against your house, setting your house on fire. That is not the case. I am convinced that all the people are wrong, and that I am the only one that is right, that lightning rods do not attract lightning. I do not doubt that sometimes you could have a picture of a lightning rod being hit by lightning, but that is not the way they function. And the reasoning is as follows. Lightning cannot jump through the air. Air is an insulator, and you cannot have a current flowing through the air. So now you know that I'm crazy. I just said that lightning doesn't jump through the air, and everybody's seen lightning jumping through the air. Well, wait a minute. It's not air that the lightning jumps through. The presence of these charges creates a field that is very, very strong. It will make the hairs stand up on your body. And you can feel that it's bad. You can feel that big field there. And when you feel it, you ought to get nervous and get away. If you were an animal, you would. But human beings tend to not pay attention to their bodies. So even though they feel something weird, they don't pay attention to it. Well, they should, or they might be dead. But that field that is so strong is strong enough to take air molecules and rip them apart. separating the positive and the negative, the air molecules into ions. And this happens, the field is most strong up here close, and so it happens here, and it happens down here close to the Earth, and these atoms get ripped apart, and they gradually build a pathway of ripped apart atoms going up from the Earth and coming down from the cloud. And when those two paths meet, and they're called leaders, when these leaders come together and make a continuous pathway of ripped apart atoms, that is when lightning moves. So there are two steps. First, the leaders grow up and down until they meet, and then the lightning moves. And it happens pretty quickly, those two steps. Well, suppose we have a lightning rod which has perhaps the strongest field of all in this region is right here close to this lightning rod. Well, if you are like charged to the lightning rod, then the field repels you. And if you are opposite charged, if you're an ion that is opposite charged, then that field attracts you. And you either come over and become neutral through an exchange of an electron, or if you were negatively charged, you might give your electron to this, which would carry it into the Earth. But the effect has been to remove all of the ions from this region, and so there are no leaders growing here. I don't know if I can get rid of the leaders. We'll just leave the leaders there. But they're not there. Because of the lightning rod, we have this field which, as soon as ions get created, air molecules get ripped apart, it gobbles up all of the ones that are opposite charge to the lightning rod, and it pushes away all the ones that are like charge. And so there are no ions, and there's no pathway, and so the lightning doesn't jump. And I will show that to you in class, and you will say, Mr. Houghton, you are a wonder worker. Thank you for speaking truth to us when everybody on the internet is trying to tell us lies.